Hello, my name is Tamara and I'm from the Education Average team here at Geoscience Australia. Throughout this video, we're going to explore the formation of earthquakes and tie this into the plate tectonics theory, how to navigate and interpret earthquake data within the Geoscience Australia Data Portal and the Earthquakes at GA Data Portal, and provide examples of how to use these resources in your classroom. So to start off with, what is an earthquake? Well, an earthquake is shaking in the ground caused by the energy released when rocks break under pressure or move. And this energy is described by the magnitude scale. And how this logarithmic scale works is that as the numbers increase, so going from a 4 to a 5 to a 6, the amount of energy of that earthquake is 30 times larger at each whole number jump. So it does quite large for some of these magnitudes of earthquakes. But how do earthquakes occur? Well, we need to take a step back and look at the world as a whole and how the earth is structured. So the earth is made up of many different layers, with that core, inner and outer core layers, building up to that mantle, that molten rock layer, out to the outermost layer, which is often described as the crust. If you're talking to a more secondary student audience, you might use the terms lithosphere for the crust or the hard, brittle part of the earth, and the asthenosphere to represent that molten rock layer below. But basically, this crust or lithosphere layer is broken up into smaller pieces, and these pieces are called tectonic plates. And the idea is that each tectonic plate can move around, traveling at different speeds and in different directions. And depending on how they move around and interact with each other determines what kind of geological events will occur, and also what types of landscape features you might observe at the surface. So earthquakes will typically occur along tectonic plate boundaries, and this map shows some of those boundaries around the world. And this is because there's lots of movement right at those edges. So it means there's lots of opportunities for rocks to break under that pressure or stress environment, which is what creates those earthquakes. However, earthquakes can also happen inside of tectonic plates, and this typically will occur along pre-existing faults or cracks, which were created from other past earthquake activity. Now, we measure earthquake energy with devices called seismometers. And what you can see here in the image is an example of a seismic station. So Geoscience Australia has approximately 150 different seismic stations all across Australia, and there's many more all across the world managed by different countries. And they're all there designed to monitor earthquakes. So these stations consist of solar panels to provide power, especially in these remote areas where they're placed, and a satellite dish to send the data to earthquake center hubs. Now, inside the hut, there is some equipment, including a computer and other instruments that can translate the data. And the most important part is there's a borehole going down so it touches the main rock present in that area. And in that hole will be the seismometer. So in this imagery, we've got the little green device, and the other golden looking device are the seismometers. Now, I can actually show an example of a real seismometer. So this is an example of an older model of a seismometer that can be used to detect going up and down motions that are going down in the ground. And how it does that is with this little metal weight right here. So how that works is that this is the part of the machine that can move around and move in different directions. So when this is placed in the ground, touching the rocks around it, and the ground begins to shake because of an earthquake, the whole device will shake with it. And as it does, that metal weight will move its position, and every time it moves, it'll send a signal down the cord, which will be collected on that computer and will be sent via the internet on that satellite dish to different hubs of where we're monitoring for earthquakes. So in Australia, we have one of these hubs here in Geoscience Australia in Canberra, and it's called the National Earthquake Alert Centre. And that image on the left gives you an idea of what that looks like if you were to step into there. So this is important because it's a 24/7 monitoring for earthquakes hub. And it's not just the data being collected from the seismic stations that we manage, but also data from across the world is shared freely from different countries' sensors. So on the blue screen with the white squiggly marks, each horizontal white mark represents one sensor somewhere in the world that is coming into the centralized hub. And that's really important because not only does it allow us to monitor earthquakes in Australia and our neighbouring countries, but because by monitoring earthquakes, we can also keep an eye on other geohazards that are triggered by them, for example, tsunamis. Now, Australia doesn't typically experience as many earthquakes nor as large a magnitude of earthquake compared to a lot of our neighbouring countries, and we'll explore a bit of why that is through the data we're going to look at today. But it's still important for us to be aware of them because it is a hazard we face. And additionally, we do have some examples in the past where we have had some more destructive earthquakes, even though their magnitudes weren't at the top of the scale. So for example, that image on the right is from the Newcastle earthquake that happened in 1989, and that had a magnitude of 5.4, sort of sitting right around in the middle of the magnitude scale. The reason this had such an impact is it happened directly on the city centre, so it was right, the epicenter was right on top of that town, but also at the time, a lot of these buildings were designed with old brick masonry and weren't reinforced to handle larger earthquakes. So it meant that some buildings were damaged more easily than they would have been in a different circumstance. So with some of that background context in mind, we're going to now jump into the first of the data portals, which is the Geoscience Australia data portal. And we're going to explore our 3D globe model, which is representing historic earthquake data from all across the world. Now, you can either go to the link that's on the slide right now, or you can type Geoscience Australia Portal into Google, and it should come up as the first link. So now, when we click onto the Geoscience Australia data portal, we can see here that we've got our map of Australia. Now, the first thing we're going to do is we're going to go up to this top right corner and we're going to select the community and education persona. This is going to allow us to see all the data sets that have been curated by the education and outreach team to suit a curriculum linked audience. So all the topics and resources we've created will link into the data set seen here. And it's also a bit more of a simplistic information and view for your students, so it's simpler for them to use. So in here, we're now going to go load our 3D model, and then we'll look at some navigation within that 3D model. So I'm going to click on the Layers tab here, and we're going to scroll down until we can see the 3D layers. Once that loads up, we're going to be looking at the Hazard Scenarios and Risks tab. Going to continue going down to the Natural Hazard Scenarios and Risks. And we're going to go down to the Historic Earthquake Global. So there's a few tabs going down, but you'll know you've hit the data set when this menu appears. And we're going to click Add to Map. And this is going to load and change our view into a 3D model rather than a 2D map model. Now, as this data loads in, this represents all the historic earthquakes across the world, and they've got their geolocation marked on the globe, but each dot representing that one earthquake event in the past. And how the color ranges work is that dark blue is a shallow earthquake close to the surface, and as it goes down the rainbow towards red, red being about 700 kilometers deep into the earth where this earthquake was detected. So we get that sort of picture. Some quick navigation things to be aware of. Any of these data portals use the same basic navigation tools. So if you click with your left mouse button and turn, you're going to change the view you're looking at. You can zoom in or zoom out depending on your scroll wheel, or using the plus and minus buttons over here. And we can zoom quite far out to see the whole globe. Some things that we need to fix in the settings to make this a bit more usable. As we can see, it's a translucent globe, and that can be a little confusing, but we can tweak that with some of the settings. So if we click on the Layers tab again in the top left corner, we've got two different sets of data that we can manipulate. The first one we're going to do is at the top here under 3D Layers. We're going to change the ground opacity until it's somewhere between 60 and 70%. What this does is it makes the map part of the data set darker and clearer to see, and allows you to still see the earthquake data, but just it sort of balances out that translucency. And you can have a play with this to whatever is your preferred percentage. The other thing we're going to do is we're going to untick Show Stars. You can see a bunch of these random white dots in the background. This is not the position of the actual stars, it's a decorative feature, and we just want to remove that because we don't need it for today. We're then going to scroll down to the actual data set we've loaded in, because there's some more targeted sliders we can fiddle with to adjust our data set. The first one being the magnitude scale over here. So we can set a particular range. We want our magnitude data to come forward. So if you're wanting to look at, 5 or larger earthquakes, or if you want a smaller range. Noting that the smallest magnitude data we have in this portal is magnitude 3 or higher. So if you're looking at anything smaller than that, you'll get no data sets. And we can see that by dragging the slider across. And then once we hit 3, there's no data set left. This is purely because there is a lot of magnitude 2s and 3 earthquakes every single year across the world, and it just would crowd the data too much. The other thing we can look at is the depth slider. So this allows you to see either the most deepest parts or some of the most shallowest parts of the data set, and you can drag it back and forth or set a range as we did with the magnitude. So now that we've got an idea of how to use some of these sliders, what I want to do now is sort of highlight the power of this model to be able to represent not only earthquake data, but relate it back to plate tectonics and how it can represent different plate boundaries. So we saw that on the map before, but on this global model, it makes it a little easier. And the way we can do that is that different types of tectonic plate boundaries will create different earthquake data patterns. So just as a recap, we've already mentioned the tectonic plates, but at those boundaries, you typically have 3 ways that plates can interact with each other. You can have 2 plates that are pulling apart, and that's a divergent boundary. And what happens there typically is that as they pull apart, you get some breaking of rocks, which creates some small, shallow earthquakes, but you also have some magma rising up from below, which will outflow over and make an underwater volcano. You can also have 2 plates that are sliding past each other, and that's called a transform boundary. And that is got a lot of potential for breaking of rocks, which creates a large cluster of shallow earthquakes. You can also have 2 plates that are colliding in some way. And there's different ways that will interact, either building up or going underneath each other, depending on the density of the rocks involved. So I'll go through a bit more detail as we get to each example, but they're the 3 boundaries we're working with: pulling apart, sliding past, or colliding in some way. So let's have a look at that right now. So to do that, we're going to zoom in and we're going to jump across to South America and Africa, and right in between those 2 areas. And what we can see here is that in between these 2 continents is this blue sort of shimming across line of shallow earthquakes. And we can follow that all the way down in between these 2 areas. What that represents is a place where there's 2 plates diverging, and we can tell that because it is a really thin chain of shallow earthquakes, and that's very characteristic of that. And so what that looks like if you were to go into that area, this would be what we call a mid-ocean ridge. So it's pulled apart, the magma has rised up and flown out as lava and created underwater volcanoes, creating a slight high in the bottom of that ocean area. It can also happen on land, and it'd be called like a rift zone in that case. But we can follow that all around past the bottom of South America and past these plates over here until we get up to North America. And this example over here highlights a transform boundary. So this is where we have a cluster of lots of shallow earthquakes all in a sort of similar area. And this is across what's called the San Andreas Fault, which is a pretty famous area for earthquakes in California, in America. And that's because that fault zone where it's sliding past each other and creating a lot of earthquakes. It might be a little hard to see, but you can always adjust your ground opacity for a time just to see that big cluster there that's collected, and then put back the map to get a better view of what's going on there. So this one's very famous, and there's been a few movies about it, so this might be one that your students easily recognize. But now I want to focus a little closer to home, so to us here in Australia. And we've got some really interesting boundaries all around us. We're going to focus on this one right here between pretty much New Zealand and Fiji and a couple of the other Pacific islands through this area. We can see that this has a clear gradient from shallow to deep. So this immediately is giving a hint as to the type of boundary going on here. This is an example of where two plates are converging or colliding. And what happens when plates collide is all around that density. So if you have continental crust or land crust versus oceanic crust, they're made of different materials, different rocks. So the land crust typically is going to be less dense, more buoyant compared to ocean crust. So if you had ocean and a land bit of crust colliding, the ocean will always go underneath the land. And in this case, a big chunk of this is just two bits of ocean. Whichever part is the older oceanic crust, it makes it colder and denser, that will go underneath the other. So it's kind of like a competition of whichever's densest is always going to subduct or go underneath the other plate. And we can see that because the earthquakes aren't staying at the surface like all the other boundaries. They are literally going into the earth. And how that works is that as it's going in, it's causing pressure in the rocks as it goes into the earth, into the layers of the earth. And more of that rocks will break and you'll get those big earthquakes happening all the way down that bit of crust. The other thing that often happens at these boundaries is that because it's going into the earth, it's disrupting that molten rock layer, and you'll start to get some magma rising up to form volcanoes through lava being released. So they're the two interactions you see at these boundaries. Now, the really amazing thing about this model is that it's a bit, you can sort of see this trend going through, but you can actually see it in a really good visual cross-section way because it is a 3D model. So to do that, rather than our left click, we're going to use our right click on our mouse, and we're going to drag up to change our view. And what this does is that we go from being looking at the face of the globe to flipping it on its side to kind of look as if we're looking into the earth. And what we can see here is that this is the shallow earthquakes, and we can see at depth all those earthquakes that are going in to the earth like this. And we can see that angle coming in. So this not only confirms it's a subduction zone, but it also actually shows us some information about the direction the plate is moving. So in this particular situation, we have Australia on this side, so the Indo-Australian plate, and we've got the Pacific Ocean plate. And what's happening there is that Pacific Ocean plate is subducting underneath our plate and going in at a bit of an angle heading towards the west. So we can see that here, that if I follow my mouse, it comes in and subducts down into the earth going to the west. And so that's a really good way to show directions of plate movement and not just what's happening at that edge. Now, this is a good way to show one example, but we've got many nearby us. So if we bring it back up and we drag across to look at Indonesia, we can see that there's also a bit of a rainbow effect going on for here. Now, you might be able to visually just tell straight away, but if your students are having trouble seeing it, especially because this one's in the middle of the globe, it's harder to get that cross-section view. What you can do is you can click on the Layers tab, and this is where we can use the depth slider to our advantage. So I'm going to drag it all the way to the left so it's as low as possible, and we're focusing on those shallow earthquakes first. And whichever direction the rainbow starts to build out in and grow in tells you the direction of the plate. So we can see it's starting shallow and it's growing into that pale blue and traveling into that green as it's heading north towards the other Indonesian islands above it. So what this is showing is that the Australian plate below has collided in with Indonesia and is subducting going north underneath the country. And we can see that slightly sharper angle than what was over here because it's a bit harder to see that gradient. So this is a really good way to model that. Now the last way that plates can interact is a collision, but where you have both continental and continental crust, where they have the same or similar densities, so neither wants to subduct. In that situation, you're getting this collision and this building up and smearing together to build up a mountain. And we can observe that as an example near us as well, because India is part of our plate and has collided in with the rest of the Asian continent. And it creates the Himalayan mountains and it creates Mount Everest through this chain. Now, in the earthquake data, there is not a lot of information here. There's a few scattered shallow earthquakes, not a lot of clear data. And the reason that's happening is that when we talk about mountain building, instead of being a sudden rip, break, or movement, it is this building up and sort of smearing together. So this is what we call a ductile deformation. It folds together rather than quickly breaks or rips. So you won't see as many earthquakes. But that can make it trickier to spot it on a model like this. So what you can do to highlight places on the map that have high elevation, they're either going to be triggered by mountain building or by volcanoes. So to do that, we're going to go back to our layers tab. We're going to go to this top area and we can see we've got this section called vertical exaggeration. So keynote here, this is going to exaggerate the terrain data significantly, and so it will be less accurate. But it's a good visual cue for your students if they don't know geographically where all the high places are in the world. The first thing we're going to do is we're going to untick link, because we don't want to change our earthquake data, we only want to exaggerate the terrain. And then we're going to drag that to somewhere around, I don't know, above 50 somewhere, just to really highlight that. And so now we can see that this is already more elevated, but if we use our right click and tilt, you can see that this is significantly elevated. And we can then compare how tall and how exaggerated that looks compared to the earthquake data around it. So not a lot of earthquake data means it's a mountain building example. However, if we go to another section, back towards South America, and we come down here where there's the famous Andes, and we can kind of see that that's significant as well. Look at that high point there. But the key difference here is that when we look at this data, I might bring it to that side bit so you can see it a little better. We can see that there is a massive cluster of shallow earthquakes transitioning into deeper earthquakes. Again, we can bring that data layer across and use our magnitude slider, our depth slider to be able to see that growth. So in this case, the Andes are not mountain building, they're created by the volcanoes that are created by that subduction zone and that remelting. So this is a really great way to talk about all those different landforms and how the earthquake data can actually tell us quite a lot about why our Earth looks the way it is, where tectonic plate boundaries are, and how those boundaries are functioning, which is all really important. So that's the first data model we wanted to highlight in this video. The second one we want to use is the Earthquakes at GA portal. So this gives you the web address if you want to go that way, but we can also Google Earthquakes at GA and it will come up as well. And this is going to explore all the data that was published by the National Earthquake Alert Centre here in Geoscience Australia. So this will highlight recent earthquakes that they're publishing actively as they're monitoring for these events, but also historic data from them and other sources that they've added in. So it will not cover every earthquake that's ever happened, but it does cover a large range of recent and historic earthquake events. So as we click across, I'm going to jump across to my new tab, which is Earthquakes at GA, and you see it looks very similar to our other data portals. So the same rules apply. You click and drag with your left mouse button to move around, and you can scroll with your mouse wheel or use the slider to do that. Now for this data set, we can see that there is data beyond Australia because we are capturing some of that global seismic systems and monitoring systems that we're a part of. But we're going to do a bit more of a focus around us as that is the theme of this video. To give you a better idea of what's going on with all these dots and what they mean, we can click on the Legend tab in the top left corner, and this is going to explain what each of those dots represent. So a red dot is an earthquake that's happened in the last 4 hours, an orange dot is the last 24 hours, and yellow is represented as older. Now, the default for this website is 7 days, but I'll show you in a moment how to change that to different time ranges. The actual size of the dots really matter in this portal, where the bigger the dot is, the bigger the magnitude of earthquake. So visually, you can straight away see whether it was a bigger event or a smaller event based off the size, and the color gives you how recent it has occurred. Now, another way to see all this data rather than visually is through the Recent Earthquakes tab in the top right corner. So this is going to give you a full list of what's going on, and this is going to give you the summary data and some ability to manipulate the recent earthquake data that you're looking at on the map. So to do that, the top one here allows you to select between 1 day, 7 days, and 30 days. So this will change not only the list, but the visuals you see on the graph. So for example, if I change it to 30 days, we're going to have a lot more dots suddenly appearing. You can set a particular magnitude. So currently it's set to all as the default, but you can change it to 2.5 plus or 5 plus if you want to narrow down that range, because it can pick up some quite small earthquakes. And you can also set whether you want the world or Australia, and that's up to you with what you're looking for. And what these will show here is the summary data for every single earthquake dot that we can see on the map. The summary data will include the magnitude of that earthquake, the depth of it, where it exactly happened on the map, and its date and time of the event. And the important thing for all earthquake data across all portals is that it is in coordinated universal time. So what that means is if you want to look at an example of a recent earthquake near you, the date and time may not match your exact time zone, and you may have to convert it to see exactly when that happened. It's just the agreed upon time that everyone across the world is using for earthquake data. Now, this allows you to see it in a full list of these different recent earthquakes, but you can also just go and click on any given dot on the map. So for example, if I click on this dot here, it's going to take me across to this earthquake, and this happened on the Tonga Islands. So it will give me the same summary details we had in the other page, where it showed where it was, its date and time, its magnitude, and its depth. So it still gives that same summary, but it also gives you a bit more detailed information. So you can go down and click on the seismograms, and what this represents is all that data collected from the seismometer I showed you earlier gets translated into this visual seismograph. And the images of these can be called seismograms. So they're all a similar thing, but the idea being that this is the visual of the energy wave of that earthquake and how it shook. So you can see that there's quite a few different ones, and they all look slightly different as well. That's because the closer you are to the earthquake event, the more compressed the energy will look on a seismogram, because it's really close. It's like captured quickly and all recorded there. If that energy has had to travel through the earth to reach other sensors, you're going to get more spread out pattern. And for earthquakes, they have a very specific pattern that identifies them as an earthquake. It builds into 3 parts of a primary wave, which is being marked out in red with the P on these images here. They have a secondary wave, which is sort of in that middle section, and then your surface wave. And that's where you actually feel the shaking of the earthquake if you were nearby. And you see each of these have a little kilometers, which shows you how far away that seismometer was from the sensor. And you see it does get really spread out when it's thousands of kilometers away versus only a few hundred kilometers away. Now, because this was in the ocean, you're going to get a much further distance to record these ones versus if it was on land where the sensors could be closer. Now, the other thing you can do is you can actually share this specific recent earthquake data. So you can click on this little button here called Share Event, and it will give you a link that gets copied to your clipboard that you can then paste or share with students or other people you want to show a specific event that's happened. And the last really important part of going into a specific recent earthquake is this button in the top right corner called I Felt This Earthquake. What this does is it allows you to bring a little citizen science into your classroom. And it's really important because what this does is taps into the second way we can describe earthquakes. And rather than using the magnitude scale, which is the energy of that earthquake calculated based off the pattern of the earthquake wave and some equations to calculate that energy, we have another scale called the Mercalli scale. And I can show an example of that on our slides. So this gives you an idea of that scale, and basically how it works is that it represents the intensity of that earthquake. What did people feel, observe, experience, any damage that occurred, and it's described in this scale form like this. So though it goes from 1 to 10, it is a different scale to the magnitude scale. So we can kind of use that citizen science where if your students or yourself have experienced a recent earthquake, you can then describe what you felt and what you saw and add that into the science around this data portal. So if we jump back, you can go through and complete this questionnaire. So there's several questions that will come up and what it looked like, what did you experience, and give details. And that can go towards that intensity scale for that event. And that can be really helpful to the scientists when we're talking through this. So this is just some of the ways you can use the recent earthquakes. And there's one more thing before I show you the search function for historic earthquakes, because we've already talked a lot about plate tectonics and how this ties in. We've already looked at legend, but if we go to the left, we can click on layers. And there's a couple extra things you can add on here. The one I want to show you today is called tectonic plate boundaries. And what it does is it marks out where those tectonic plate edges are. Now, to figure out what the colors mean, if you click on this little button next to it, which has like a little legend button, it will show you that green represents diversion or pulling apart, transform is red, sliding past, and blue is convergent. So that's typically going to be a subduction or a mountain building thing. And then you can see all across the world where each of those plates are, and you'll often find that all these earthquakes are typically going to be along one of those edges with a couple anomalies that are inside the plate, like in Australia. So that's another really good visual tool when you're talking about this in a 2D model versus a 3D model. I'm going to turn it off for now, but I just wanted to highlight it to you as a resource you can use. This has been mostly just summarizing what you can broadly see in the main part of this website and the recent earthquakes. The last thing we want to tap into is the power of the historic data that's been collected over time from every earthquake being published and being stored in this website. And that means it's a great source for just raw, real scientific data that you can use in your classroom. You can do interpretations with it. You can look at trends over long periods of time, so 50 to 100 years. And it just helps discuss a lot of that key curriculum point around interpreting, collecting, and understanding data. And that covers science, maths, and a bunch of other subjects. So to do that, we're going to go to the top right corner and we're going to use the search function. So for this, we're going to be looking at different ways that you can customize a search to have a set of data that you can then interpret and manipulate. One thing to note just before we go through the actual criteria in this list, there is one section here called recent earthquakes. This is just another way that you can see the recent earthquakes that are on the map. It has nothing to do with the actual search criteria. It's just highlighting, again, another way you can see the dots or the data points that could be present on your map. So you can just ignore that completely if you're trying to search for some historic data. So going down in order now, the different things that you can select. You can choose between Australia or the world, noting that there's a lot more data present for Australia because we are the National Earthquake Alert Centre in Australia, and that's where the emphasis is in, and we have more sensors in Australia that we are able to trust and monitor. But you can still look at some world data sets. We have a magnitude range, so for this example, I'm just going to set it for any earthquake that is 4 or larger, and going up to 9.9, which is larger than the largest earthquake we've had, but it's just the maximum number that can go in that box. Now you can set a date range, so for example, you can either click on the calendar to pick a time, or you can just select a year and type it in yourself. So for example, let's just go about 10 years back. So if we go the 1st of, let's go 1st of the 1st, and we'll go 2015, just an example. Now to lock that in, you have to click elsewhere on that panel, otherwise it may forget what you've typed in, just as a tip. And maybe I don't want today, I actually want to go back to the start of this year, and we'll do it exactly for 10 years, starting on Jan 1st, and again, click away to lock in your date and time. Now, you also have some criteria where you can set exactly where you want this data to be covering. So currently it's just set to the whole of Australia, but you can set to a specific state, or you can even draw your own custom shape on the map that you want to mark out. So for example, if we wanted to just do a box area down here, we can click draw, and we can just cover several states or several areas depending on what we want to look at. For my example today, I just want to focus on the state of Victoria, just because I know that they've had some interesting earthquakes in the past little while. Sometimes it does that to spin around. Sorry if that was a bit quick for you watching there, but it's going to zoom in on that area that we've asked for. And the final thing you can edit is the number of results per page. If you think there's going to be quite a few results, you can put as many as you want there, but it will allow you to search through and alter that. And then we click search. So as it does this, it gives us our table, but it also marks out all the dots on the map from what we searched for. So we can see the total results at the top, that there was 8 results in the last 10 years that were a magnitude 4 or higher in Victoria. And currently it's set to the date and time in order of when these events occurred. You can customize any of these table headers to be the bit that it's sorting the data by. So what I recommend, if you're trying to find, for example, the largest earthquake that's happened, then you would click on the magnitude, and you'll see this little arrow has come up and it's pointing down. That means that it is showing smallest to largest magnitudes in order. Because our list is only 8 long, it doesn't really matter for this example, but if you had a list that was hundreds of pages long and you wanted to know the largest, if you click it again, it will swap it to the largest being at the top. So you can even customize how your data is sorted on this page and skip through to different pages as needed. Anything on the list, you can click on an event and it will take you to that specific event, or you can click on the map and it will also do the same as what we saw with the recent earthquakes. So let's go look at the biggest event that we can see here. So this is again going to provide the same summary detail that we had in the recent earthquakes, it's just a historic event instead. So we can see that we have our date, our time, our depth, our magnitude, and all those details, and where it's located on the map. Now, the thing that's really interesting, especially for bigger events, is that often these events are felt quite widely across Australia, and we can actually see that data that is collected from that felt report that we looked at in the recent earthquake. So down the very bottom, we see these 3 boxes down here. I'm going to click on felt reports, and this is going to show on the map where every report was made from clicking that I felt this earthquake button. Now, anything that's a star is one report. Anything that's a circle with a number represents a cluster of reports. And when I hover over it, you can start to see those individual stars. So this earthquake happened in Rawson in Victoria, a bit more regional to the main Melbourne CBD. And this was felt so widely that we have felt reports in Tasmania, Adelaide, up to Brisbane even. So this is quite a significant event. Though it didn't cause a lot of damage, it was very widely felt. And we can see that just by the fact that there's reports there. But the really powerful thing is by taking all the answers to the questions provided, we can actually create a shake map. And this provides that gradient representation of intensity based off the data collected and based off that Mercalli scale that we can see down here. So we can see the epicenter of where it happened, where it's more that orangey yellow colors. So it was like a medium sort of strong feeling earthquake based off what was observed, and then that weaker feeling as it went further out and across. Now, this is a really great visual, and it's a great way to get your students interpreting a different style of data where it's this gradient representation of intensity rather than just a list of data points. that they could potentially then graph or do their own analysis on. Noting that the gradient does fill in the gaps where there may not have been a felt report, but it assumes it's still similar in a similar area. If you want the very targeted version, which shows exactly where those felt reports data sits, you've got the felt grid. And that can give you that more exact data, but maybe it may be less helpful depending on what you're looking at. So this is just some of the many different ways that you can use Geoscience Australia data portals in your classroom to talk about earthquakes, plate tectonics, and just how to manage, collect, and interpret data in a lot of different ways. If you check in the details description of this video, you'll be able to find some links to some classroom activities and other resources that we have created to complement these portals and get you using it in your classroom a bit easier. But thank you so much for tuning in to the video today.